First, let's briefly go over the rules that we use to analyze operational amplifier behavior. The Opamp circuit schematic symbol is shown here. Op-amps typically have 5 or more terminals. The op-amp has 2 inputs, here, and one output here. The ideal operational amplifier rules is that there's no voltage difference between the input terminals, so this delta V, Vp minus Vn, is 0 volts. There's also no current flowing into the input terminals, so Ip and In are also both 0. 2 of the terminals, V plus and V minus, are used to provide power to the operational amplifier. The op-amp will not function if you don't apply power to these terminals. To complicate things a little, these terminals are sometimes not even evident on circuit diagrams. We just assume that they're there and let it go at that. When we analyze ideal op-amps, we generally don't assume anything about the voltage and the current at the output terminals. However, there are some practical limitations associated with these parameters. The output voltage is restricted by the limits defined by V plus and V minus. V out has to be strictly less than V plus and strictly greater than V minus. In fact, you usually can't get to within about a volt or 2 of the supply voltage before the op-amp saturates. The output current, I out, is limited by the design of the op-amp itself. The op-amp we will use provides relatively little current, but higher current devices are available. Finally, there's one very important point relative to the voltages on this diagram. All of the voltages should be relative to the same reference voltage. In general, this will require that you physically interconnect them to ensure a common reference. Op-amps come in a lot of different varieties. We will use an LM741 op-amp. So I want to spend a little time talking about the physical pin descriptions for this particular operational amplifier. The general comments I'll make for this op-amp will be typical of most operational amplifiers, but the specific pin descriptions may vary from op-amp to op-amp. In order to find the pin descriptions for any given op-amp, simply look up a datasheet online. One of the first pieces of information on the sheet will generally be a picture similar to this one with a description of the pin functions. First, a couple of comments about operational amplifiers in general. Op-amps which can be used in a solderless breadboard are generally what are called dual inline packages, or DIPs for short. This simply means that the pins are connected in 2 rows of pairs, here and here. The spacing of the pins allows the chip to be inserted in a solderless breadboard with the central channel of the breadboard separating the rows. This ensures that any pin is electrically isolated from any other pin. Second, the orientation of the pins is specified by a notch like this at one end of the chip, or a dot in the corner of one end of the chip. Many chips have both of these indicators. If you're looking down on the chip so that the notch is at the top, pin 1 will be in the upper left-hand corner. Other pins are numbered successively in a counterclockwise direction. So 1, 2, 5, 6, up to 8. Now let's take a look at some physical op-amps themselves. This is the LM741 op-amp. The op-amp type is printed directly on top of the op-amp. It has 8 pins in 2 rows of 4 each. It can be inserted in a solderless breadboard like this. The central channel of the breadboard is straddled by the op-amp. The notch is at this end of the op-amp, so this is pin 1. The other pins are numbered counterclockwise. The pin descriptions for the LM741 op-amp are shown again here. Pins 2 and 3 are the inverting and non-inverting inputs respectively. Pin 6 is the output terminal. So if I sketch the op-amp schematic on this picture, it'll look something like this. This pin goes to the inverting input terminal of the op-amp. This pin goes to the non-inverting input terminal, and this pin goes to the output terminal. The positive voltage supply is at pin 7, and the negative voltage supply is pin 4. So this would be connected to V plus on the schematic, and this is connected at V minus on the schematic. Pins 1 and 5 are offset voltage trim terminals. These can be used to fine-tune the op-amp behavior, but we won't use them in this lab. Finally, pin 8 doesn't do anything. It is said to be not connected, or NC. On our physical op-amp, pin 2 is the inverting input, pin 3 is the non-inverting input, and pin 6 is the output. The positive voltage supply is pin 7, and the negative voltage supply is pin 4. We'll always need to provide power to the circuit, so I'll go ahead and connect the voltage supplies now before we wire up the rest of the circuit. By default, on the Rex Qualis power supply, the breadboard holes with the blue stripe are the reference voltage. So I set up the power supplies relative to those voltages so the power supplies share the same reference as the input voltages. I'll use 9-volt batteries as the power supplies. For the positive power supply voltage, I'll connect the positive terminal of the battery to pin 7 and the negative terminal of the battery to the blue power strip. For the negative power supply, I just interchanged the terminals on the battery. Now the positive terminal of the battery is connected to the blue strip of the breadboard, and the negative terminal is connected to pin 4. The circuit now looks like this. I generally connect my power supplies first, since my experience has been that forgetting to connect these is my #1 silly mistake when wiring up op-amp circuits. As an example for this video, we'll create this inverting voltage amplifier circuit and investigate its response. If we analyze the circuit, we'll find that the output voltage, Vout, is just the negative of the input voltage. The feedback resistor and the input resistor have the same values. We've already connected V plus and V minus to the positive and negative voltage supplies, so all that remains is to add the resistors to the circuit and apply an input voltage. We'll use the Rex Qualis power supplies to apply the input voltage, Vin, to the circuit. Also, I want to reiterate that all the voltages, V plus, V minus, Vin, and Vout, have to share the same reference. According to our circuit schematic, we connect a 1 kilo ohm resistor between the output terminal, pin 6, and the inverting input terminal, pin 2. We connect another 1 kilo ohm resistor from the inverting input to one of the Rex Qualis power supply strips. I'll use a 3.3 volt power supply. To do that, I place the jumper in this position, which provides 3.3 volts at this bus strip. The final step is to ground the non-inverting input. I connect pin 3 to one of the blue strips on the breadboard. Now let's zoom out so I can see my DMM. To measure the output voltage, I'm measuring the voltage between the output terminal at this terminal of this feedback resistor relative to ground, which is any of the blue stripes on the breadboard. Turning on my DMM, I get about negative 3.4 volts, which is almost exactly the opposite of what I would expect from my input voltage, which is a positive 3.3 volts. To get a better idea of whether this is accurate or not, I should probably measure the input voltage.